Hello everyone. Over the last week, we have discussed about various seismic design philosophies in which we have looked into performance based seismic design in detail. The objective of the performance based seismic design was to attain desired seismic performance of any given building with certainty. In the performance based design, we also looked into capacity based design, where we talked about hierarchy of collapse. The hierarchy of collapse is established based on the ductility of various members. The ductile members are expected to fail first, while the brittle members are expected to be stronger than the ductile members. In this week, we will look into design and ductile detailing of reinforced concrete buildings. In today's class, we will discuss about various concepts and material specifications related to seismic design of RC buildings. As we proceed with our discussion into seismic design of reinforced concrete buildings, we need to first understand what are the different lateral load resisting systems in case of RC buildings. Lateral load resisting systems comprise those parts of the structures which participates in resisting forces induced by some lateral effects, earthquake in this case. In other cases, it might be wind as well. So, in context of reinforced concrete buildings, the most popular lateral force resisting system is the moment resisting frame. Another lateral load resisting system is a structural wall, or commonly called as shear wall systems. Then we can also have a dual system which can comprise of moment resisting frame and shear wall systems combined together. In this slide, in the first photograph, we can see a moment resisting framed structure. What we can observe that the building comprises of columns and beams, both rigidly connected with each other at these beam column joints. These rigid joints are called as moment joints because they are able to transfer moment from beams to columns, and therefore this structural system is referred as moment resisting framed system. In the second photograph, we can see that there is a vertical wall made up of reinforced concrete, and this is called shear wall or structural wall. This is different from the infill walls which we build in case of moment resisting frames. Okay. We can also have a third structural system which can comprise of dual systems, in which we will have beams and columns representing moment resisting frames and structural walls or shear walls in addition to those columns. So, let us look into these structural systems one by one. Moment resisting frame systems, as the name signifies, it comprises of a three-dimensional structural system which is composed of interconnected members without structural walls, and in this case this functions as a complete self-contained unit with or without aid of horizontal diaphragm or floor bracing system. What are horizontal diaphragms? Horizontal diaphragms are nothing but your slabs. So, there can be slabs which are available in most cases. There can be some segments where there is no slab or discontinuous slab. For example, in case of staircase, floor bracing systems comprise of some structural braces in the slab. So, these are commonly used when you have large spans, when you need large column free spaces. Then in this case of moment resisting frame systems, members resist gravity and lateral loads primarily by flexural actions. It means that members are able to transfer moment from each other, which means from beams to columns. Further, these moment resisting frames can be classified into two types: ordinary moment resisting frames and special moment resisting frames. ordinary moment resisting frames, or commonly called as OMRF in short. These frames are ordinary in nature by the context of spatial ductile detailing, which means though these OMRF frames are designed to conform to IS 456 guidelines, which is the design code for reinforced concrete structures, these frames do not meet the spatial ductile detailing requirements which are given in IS 13920. On the other hand, special moment resisting frames, commonly called as SMRF in short, they need to conform to both IS 456 and IS 13920 guidelines, which means apart from satisfying the conventional design of reinforced concrete structures, these SMRFs also meet the spatial ductile detailing requirements which are required for seismic resistance. Therefore, in regions of high seismicity, which are referred as higher seismic zones as per our Indian standard, in those regions we will be constructing SMRFs. Now let us look into structural wall and dual wall systems. So the second prominent type of structural system in case of reinforced concrete building is the structural wall or shear wall system, which comprises of vertically oriented planar elements called structural or shear walls. These are different from the infill walls that are used in moment resisting frame. Infill walls usually comprise of brickwork. It can be of red brick, it can be of aerated autoclave concrete blocks, it can be fly ash bricks or anything of that sort put with mortar or suitable adhesive. But in this case, the structural wall or shear wall comprises of reinforced concrete. It has good strength of concrete as well as it has use of reinforcement, steel reinforcement. Now, these shear walls can again be classified into two types: ordinary shear walls and special shear walls. While ordinary shear walls are primarily designed to resist lateral force effects such as axial force, bending moment and shear force in its own plane, the special shear walls, apart from this design, they also meet special ductile detailing requirements. Now, these special ductile detailing requirements, which are important from earthquake resistance perspective, is given in IS 13920. In the code IS 1893, you will find these structural systems named as OSW and SSW, ordinary shear walls and special shear walls. Now, you can also have systems which will comprise of a combination of moment resisting frame as well as structural or shear walls. When do you need such dual systems? If you need to increase the stiffness along one of the directions for a moment resisting frame, what will you do? You will build a shear wall between two columns in that direction, and therefore these systems are also quite commonly used. Modern day structures, rather than being based on only structural walls, they rely on dual systems. So now, having discussed these, let us discuss about the hierarchy of collapse in these systems. In the moment resisting frame systems, the first failure is expected to happen as plastic hinge formation in beams. Why? We have already discussed as part of the previous week in the capacity based design, that is, the collapse of one beam does not lead to catastrophic failure of the structure as a whole. So therefore, the first failure is expected to be in the beams in the form of plastic hinges, not the shear failure. Shear failure is still a brittle mode of failure, so that is to be restricted. After the plastic hinges form in the beams, if any failure is further to happen, then it has to be plastic hinge formation in the ground story column near the base of the structure, and then only we can allow plastic hinge formation in the upper story columns, and plastic hinge formation in foundation is not at all expected. So that was our capacity based design or the hierarchy of collapse, which we have discussed in the last week as well. Now when it comes to structural wall or shear wall systems, in this case we again want ductile mode of failure, which is the flexural failure or the bending failure of these walls. We do not want the shear failure to happen in these walls because that is a brittle mode of failure. Having said so, now let us try to understand the specifications related to various materials used in reinforced concrete buildings. So the most important material when it comes to RC buildings is the structural concrete. Why are we calling it structural concrete? Because you can still have non-structural concrete which will be used for making aerated autoclave concrete blocks or double AC block as commonly told. So what we are looking into is the structural concrete which is used to construct beams and columns as well as slabs. Now since we are using IS 13920 2016 version, as the new code is still not out, so this code is based on IS 1893 part 1 2016. That time the 2016 code for IS 1893 comprised of general provisions and buildings in part 1 itself. So since IS 13920 2016 is based on IS 1893 part 1 2016, therefore the seismic zone classification in all these material specifications will be as per the zones listed in IS 1893 part 1 2016, which means that time we had only 4 zones, zone 2, 3, 4 and 5. So that's why I have placed a map of India which shows different seismic zones from zone 2 to zone 5. So in seismic zone 2, for all the buildings we need to have minimum M20 grade of concrete, while in higher seismic zones, that is zones 3, 4 and 5, the buildings with less than 15 meter of height can have M20 grade of concrete, but for buildings which are higher than 15 meters we need to use M25 grade of concrete. Again, apart from these guidelines, we also need to satisfy IS 456 guidelines for minimum grade of concrete based on exposure conditions. So in IS 456 2000, if you look into table 5 of the code, you will find that we have prescribed minimum grades of concrete based on exposure conditions. For example, in coastal areas where your exposure condition is extreme or severe, then in that case your minimum grade of concrete can be higher than these specified grades of concrete. So therefore you need to satisfy those guidelines as well. I suggest you to keep all these Indian standards handy with you at your desk so that you can make the most use of this course. Now let us look into the material specifications related to steel reinforcement. In this figure we see the stress strain plot for mild steel and the high strength steel. For mild steel the curve is shown in blue and for high strength steel the curve is shown in red. As you can notice, mild steel is far more ductile than the high strength steel. So if you are using any steel reinforcement which has grade up to Fe415, that is the yield strength of 415 megapascal. Again, Fe415 is also a form of high strength steel only. So either Fe415 or Fe250 if you are using, then it needs to conform to IS 1786 2008. You need not check any other property for that. You need to know what is the characteristic yield strength if it is up to 415 megapascal. The confirmation to this code, which gives you further more tests, you can use that steel reinforcement. But when it comes to higher grades of steel, let us say Fe 500 or Fe 550, then in that case only conforming to the guidelines in IS 1786 is not sufficient. In that case, we need to also measure the elongation in the steel reinforcement bar. Elongation is represented by the strain value. So, the minimum elongation that is desired in steel reinforcement bars is 14.5%. If you find any steel bar which has elongation less than 14.5%, you need to reject that lot for seismic resistance. You cannot use that in buildings which are being designed for seismic resistance. Furthermore, there is another provision in IS 13920. These provisions are listed in clause 5.3. So, there you can find that the actual 0.2% proof stress of steel bars must not exceed characteristic 0.2% proof stress by more than 20%. Let us try to decode this. 0.2% proof stress. What is this term? Since for high strength steel we do not have a well defined yield point, we define the yield point to be at 0.2% proof stress. So, from the strain value of 0.2%, you draw a line parallel to the initial slope of the stress strain curve. That line, when it intersects the stress strain curve, at that point whatever you find the value of stress, that is your 0.2% proof stress, which is also considered as yield strength of steel in that case. And then the characteristic 0.2% proof stress represents the value of proof stress which is at least sufficed by 95% of the samples. Now, from that characteristic value, the actual value should not be more than 20%. I have also written it over here, that is the yield strength actual should be less than or equal to 1.2 times of yield strength characteristic. Now, why is it important? Why we should not have any steel bar which has more than 20% offset in this case? Because if its actual proof stress value is very high, then in that case the ultimate moment carrying capacity of the beam in which this steel is used will further increase. If your ultimate moment carrying capacity of the beam increases, then the beam will find it difficult to develop plastic hinges, and if it finds difficult to form plastic hinges and the column finds it easier to form plastic hinges, then in that case plastic hinges will get formed in column, which will lead to undesirable failure mode, that is, that will not be following our capacity based design of weak beam strong column hypothesis. That is why we want our actual 0.2% proof stress of steel bar to be within 20% plus of the characteristic value. Further on, we also need the actual ultimate tensile strength to be at least 15% above the 0.2% proof stress, which means that the strength value or the stress value at F should be at least more than 15% over the stress value at E. This is important because this will help us have stable post tilt behavior and enough deformability so that your failure is ductile in nature. So far we have discussed about different material specifications for good seismic resistance in buildings. In the next class we will define a problem statement where we will start our design of a reinforced concrete moment resisting frame, which will pave our way to design and ductile detailing of different members of reinforced concrete building. Thank you.